Hey, welcome back to Stardrift FM. It's late, the sky is dark, and tonight we're going somewhere we can never come back from. Get comfortable, this one's going to be a ride. Imagine falling into the darkest place in the universe, a place where gravity is so intense that not even light can escape, where time itself slows down, stretches, and eventually stops. Tonight on Stardrift FM, we're going somewhere no human has ever been. Somewhere we can never return from. We're going inside a black hole. But here's the thing, what we find there might not be what you expect. Because the latest physics is telling us something strange. The terrifying singularity at the center, it might not exist at all. Let's drift into the darkness together. Let's start with the basics. A black hole is what happens when gravity wins, completely, absolutely, without compromise. When a massive star, we're talking about 20-30 times the mass of our sun, runs out of fuel, it can no longer push back against its own weight. The core collapses. In less than a second, matter that once stretched across millions of kilometers crushes down into a space smaller than a city. The result is an object so dense, so gravitationally powerful, that it warps the fabric of space and time beyond recognition. Think of space-time as a stretched rubber sheet. A star makes a dip. A neutron star makes a deeper dip. But a black hole? A black hole doesn't just dip, it punches through. A black hole has several distinct regions. Let's map them out. Before you even get close to a black hole, you'll encounter the accretion disk, a swirling ring of superheated matter spiraling inward. Gas, dust, and debris from nearby stars orbit at nearly the speed of light, heated to millions of degrees. This is why black holes, despite being black, are often the brightest objects in their galaxies. At about 1.5 times the event horizon radius, there's a region called the photon sphere. Here, light itself can orbit the black hole. If you were standing here and looked straight ahead, you'd see the back of your own head. Think about that. Light, the fastest thing in the universe, trapped in a circular orbit around pure gravitational power. Now we reach the event horizon. This is the point of no return. The event horizon isn't a physical surface. You wouldn't feel yourself crossing it. There's no wall, no barrier, no sign that says, "Abandon all hope." It's a mathematical boundary, the distance from the center where escape velocity equals the speed of light. Once you cross it, every possible path through space-time leads inward. Even if you fired your rockets at full power, pointed directly away from the center, you would still fall in. Because inside the event horizon, away from the center is no longer a direction in space. It's a direction in time, and you can't travel backward in time. The size of the event horizon depends on the black hole's mass. For a black hole with the mass of our sun, the event horizon would be about 6 kilometers across, roughly the size of a small city. For the supermassive black hole at the center of our galaxy, Sagittarius A star, it's about 12 million kilometers, smaller than Mercury's orbit around the sun, yet containing 4 million solar masses. Now let's take the journey. What would actually happen if you fell into a black hole? The answer depends entirely on the size. For a stellar mass black hole, death comes quickly and violently through a process with an almost comical name, spaghettification. Because the black hole is relatively small, the difference in gravitational pull between your feet and your head is enormous. If you fell feet first, your feet would be pulled much harder than your head. You'd be stretched vertically and compressed horizontally. You wouldn't be torn apart by the event horizon. You'd be shredded long before you reached it. Your body would be drawn out into a thin stream of atoms, a cosmic strand of spaghetti spiraling into oblivion. Here's something counterintuitive. Falling into a supermassive black hole would be much more survivable, at least initially. Because the event horizon is so far from the center, the tidal forces at the horizon are actually quite gentle. You could cross the event horizon of a billion solar mass black hole and feel nothing unusual. No spaghettification, no dramatic death, just the quiet realization that you can never leave. In fact, for the largest black holes, You might survive for hours inside the event horizon before tidal forces became deadly. Hours of falling through warped space-time, knowing your fate but unable to change it. Now we need to talk about time. Because near a black hole, time doesn't behave the way you're used to. Einstein's general relativity tells us that gravity slows down time. The stronger the gravity, the slower time passes. Near a black hole, this effect becomes extreme. If you were hovering just above the event horizon and looked back at the universe, you'd see everything happening in fast forward. Stars would be born and die in what felt like moments. Galaxies would spin like pinwheels. Billions of years could pass in the outside universe while only hours passed for you. And from the perspective of a distant observer watching you fall, they'd see you slow down. Your movements would become sluggish, your radio signals stretched into longer and longer wavelengths. As you approached the event horizon, you'd appear to freeze, your image growing dimmer and redder until you faded from view entirely. You'd never actually see someone cross the event horizon. From the outside, it takes literally forever. But from your perspective, you'd sail right through, noticing nothing special at the boundary itself. This is one of the strangest aspects of black holes. The journey takes different amounts of time depending on who's watching. According to classical general relativity, Einstein's original theory, every path inside the event horizon leads to one place, the singularity. The singularity is a point of infinite density. All the mass of the black hole compressed into zero volume. A place where space-time curvature becomes infinite. Where the equations of physics produce nothing but infinities, and infinities in physics usually mean we've made a mistake somewhere. At the singularity, our understanding breaks down completely. General relativity, the theory that describes black holes so beautifully, collapses at the very center of its greatest prediction. The math stops working, the physics gives up. For decades, physicists have treated the singularity as a kind of here be dragons, zono, a place we know exists mathematically but can't actually describe physically. But here's where it gets interesting. Because the latest research suggests the singularity might be a mathematical artifact, not a physical reality. The singularity represents a fundamental conflict in physics. General relativity, which governs gravity and large-scale structure, predicts the singularity must exist. Quantum mechanics, which governs the very small, says it can't, because quantum mechanics doesn't allow particles to be localized to a single point. Heisenberg's uncertainty principle states that you cannot know both the exact position and exact momentum of a particle simultaneously. The more precisely you know one, the less precisely you could know the other. At the singularity, we're talking about infinite precision in position, everything at exactly one point, which would require infinite uncertainty in momentum. This is physically meaningless. Moreover, there's a smallest meaningful length in physics, the Planck length, about 10 to the power of negative 35 meters. Below this scale, the very concept of space breaks down. You can't have a point smaller than the Planck length in any physically meaningful sense. So what's really at the center? In the past few years, physicists have proposed several alternatives to the classical singularity. Let me walk you through the most compelling ones. In a theory called loop quantum gravity, space itself is made of tiny, discrete chunks, like pixels in a video game, but at the Planck scale. When matter collapses, it can't compress beyond a certain point because there's a minimum unit of space. Instead of a singularity, you get a Planck star, an incredibly dense but finite object at the center. The pressure from quantum effects pushes back against gravity, preventing complete collapse. String theory offers another solution, the fuzzball. In this model, the entire interior of a black hole is filled with tangled strings of energy. No empty space, no singularity. The surface we call the event horizon is actually the edge of this stringy fuzzball. Every black hole would have a unique structure, like a fingerprint, encoded in the configuration of its strings. Just recently, researchers showed that modifications to Einstein's equations, modifications predicted naturally by quantum gravity, can create black holes without singularities using pure gravity alone, no exotic matter required. In these models, the collapse stops at some small but finite radius. The singularity is replaced by a highly warped but static region. The curvature is extreme but finite. An observer could theoretically survive there, assuming they could handle the enormous but not infinite tidal forces. Perhaps the most mind-bending proposal. What if the singularity isn't an ending, but a beginning? Some physicists propose that black holes transition into white holes, hypothetical objects that are the time reverse of black holes. Instead of pulling everything in, white holes push everything out. In this model, matter falls into a black hole, reaches what would be the singularity, undergoes a quantum bounce, and emerges in a white hole, possibly in another region of space-time, or even another universe entirely. The black hole's interior becomes a tunnel, not a tomb. In 1974, Stephen Hawking made a discovery that shocked the physics world. Black holes aren't completely black, they glow. The explanation involves quantum mechanics at the event horizon. In quantum field theory, empty space isn't really empty. It's a seething foam of virtual particle pairs, constantly popping into existence and annihilating each other. At the event horizon, something strange can happen. A virtual pair appears right at the boundary. One particle falls in, the other escapes. The escaping particle becomes real, and it carries away a tiny bit of energy from the black hole. This is Hawking radiation, and over vast timescales, it causes black holes to evaporate. The smaller the black hole, the hotter it burns and the faster it evaporates. A stellar mass black hole would take about 10 to the power of 67 years to evaporate, far longer than the current age of the universe. But it will happen eventually, and in its final moments, a black hole would release all its remaining energy in a flash of gamma rays, a dying scream in the darkness. Hawking radiation creates one of the deepest puzzles in modern physics, the information paradox. When something falls into a black hole, a bluk, a star, you, all the information about its quantum state seems to be lost. And when the black hole eventually evaporates, Hawking showed that the radiation coming out is completely thermal, completely random. It contains no information about what fell in. But quantum mechanics has a fundamental rule: information can never be destroyed. It could be scrambled, hidden, made practically impossible to recover, but it must still exist somewhere. So what happens to the information? This paradox has driven decades of research. Current thinking, supported by recent calculations, suggests that information is somehow encoded in subtle correlations in the Hawking radiation. Scrambled beyond any practical hope of recovery, but technically preserved? The black hole, in this view, is the ultimate information scrambler. Everything that falls in gets smeared across the horizon, then slowly leaked out in an encrypted form that would take longer than the age of the universe to decode. Here's a thought that might keep you awake tonight. Some physicists seriously propose that our entire universe might exist inside a black hole. The map is suggestive. The observable universe has a certain radius, about 46 billion light years, and a certain mass, roughly 10 to the power of 53 kilograms. If you calculate the Schwarzschild radius of that mass, the size of a black hole with that much stuff, you get about 46 billion light years. We live inside a sphere whose size matches what you'd expect if it were a black hole. In this model, the Big Bang wasn't the beginning of everything. It was matter from a parent universe collapsing, bouncing at the quantum limit, and exploding outward to create our cosmos. Every black hole in our universe might birth a new universe inside it. We might be one link in an infinite chain of nested realities. Is this true? We don't know. We may never know. But the mathematics allows it. For most of the history of black hole physics, we had no direct images. Black holes were mathematical predictions, inferred from their effects on nearby matter, but never seen. That changed on April 10, 2019. The Event Horizon Telescope, a network of radio dishes spanning the entire Earth, captured the first image of a black hole's shadow. the supermassive black hole in galaxy M87, 55 million light-years away, containing 6.5 billion solar masses. What we see is the shadow, the dark region where light cannot escape, surrounded by the glowing ring of superheated matter in the accretion disk. The ring is brighter on one side because of relativistic beaming. Matter moving toward us appears brighter due to special relativity. In 2022, we got an image of Sagittarius, a star, the black hole at the center of our own galaxy. 4 million solar masses, 26,000 light-years away. Our local monster. These images confirm that black holes behave exactly as general relativity predicts, at least from the outside. The interior remains hidden, possibly forever. So what's inside a black hole? The honest answer is, we don't know. And we may never know directly, because any probe we send in can never send information back out. But physics is giving us clues. The classical singularity, that point of infinite density, is probably not real. Quantum effects almost certainly prevent complete collapse. Something survives at the center, a Planck star, a fuzzball, a quantum bounce, a passage to somewhere else. Black holes are not just destroyers. They may be transformers, taking matter, energy, and information and converting it into something we don't yet understand. Perhaps even into new universes. The darkness at the heart of a black hole isn't empty. It's full of mystery, full of possibility, full of physics we haven't yet discovered. And that's what makes them beautiful. This has been Stardrift FM. Keep looking up.